Hello, chemistry students. We are now ready to review for the test over gases, and so I want to let you guys know there are a total of 10 questions. We're going to have 3 multiple choice questions, a question related to Boyle's law, a question related to Charles' law, a question related to Gay-Lussac's law, a question that talks about the combined gas law, the molar volume problem, a problem that involves the ideal gas, Pivnert, and we have a gas-stoich problem. And so what I'd like to do now, I want to go over each of these types of problems, and so if you understand basic algebra, this should not be any problem. I do also want to remind you that in order to get full credit on the test, you will need to show your work. You'll need to circle or box in your answer, and don't forget the appropriate unit. And so you need to have all those in order to get full credit. And so let us start then with a Boyle's law problem. And so Robert Boyle, one of the founders of chemistry, discovered a relationship between the pressure of a gas and its volume. And so it can be expressed in a very simple way. We have for Boyle's law, P1 times V1 equals P2 times V2. So P1 times V1 equals P2 times V2. So we can see that pressure and volume are inversely related. So as one goes up, the other one has to come down. And so let's take a look at a problem that uses this. And so the problem here, what is the new pressure of a gas at 0.82 atmospheres and 2 liters is compressed into a 1.0 liter vessel. All right, so again, the question, what is the new pressure of a gas at 0.82 atmosphere and 2 liters? It's then compressed into a 1 liter vessel. So notice that the volume is decreasing, and so you would expect that the pressure should increase. And so remember, pressure and volume are inversely related. So as one goes up, the other one has to come down. And so let us go ahead and set this up. What I'm going to go ahead and do, I'm going to rearrange my equation so that I can solve for what I'm looking for. I'm looking for the new pressure, which is going to be represented by P2. So what I need to do is get rid of this V2. I need to undo this multiplication by dividing both sides by V2. So I'm going to rewrite Boyle's law to solve for P2. P2 equals P1 V1 over P V2. All right, so I rearrange this so I can solve directly for P2. P1 times V1 over V2. I'm going to go ahead and plug in what I'm given. So P2, I'm going to have 0.85 or 82 atmosphere, 2.0 liter, and I'm going to divide that by 1.0 liter. Now, the beautiful thing about this problem is if you notice, you're dividing by 1, so whatever you get up here at the top is going to be your answer because any number divided by 1 is that answer. So we're going to take 0.82 and we're going to multiply that by 2. And so 0.82 times 2 is going to be 1.64 atmosphere. So P2 equals 1.64 atmosphere. All right, so notice I showed my work, I got my answer, and I got the unit. And so this should hopefully make sense because if you notice, we're taking the volume and we're cutting it in half. And so if we're cutting the volume in half, the pressure therefore should double. And notice that in fact, it does in fact double. And so that is an example of a Boyle's law problem. So now let's go ahead and take a look at an example of a Charles's law problem. All right. What Charles was investigating was the relationship between a volume of a gas and its respective temperature. And so I gotta remind you, when we're dealing with temperature with gases, we have to convert to the Celsius scale to the Kelvin scale. So I'm going to go ahead and remind you again, in order to go from Celsius to Kelvin, you simply add 273. So K equals degree C plus 273. And so that will work for any temperature conversion. All right. And also remember that Charles's law states that V1 over T1 equals V2 over T2. And so, again, we're going to hold the pressure constant, which is why it's not there. All right. Let's take a look at an example of a Charles law problem. And so the question, what is the original temperature of 250 mils of gas that is moved to 400 mils at 25 degrees C. All right, so this question is looking for the original temperature of 250 mils of gas that is moved to 400 mils at 25 degrees C. So notice that we're looking for the original temperature, which is going to be T1. And so if we're looking for T1, I can rearrange this equation by saying T1 is equal to V1 times T2 over V2. And so I just went ahead, I rearranged this equation to then solve for T1. All right, T1, my volume, my original volume is 250 mils. My new temperature, and again, I have to remember to convert between Kelvin and Celsius, and so I have to add 25 plus 273. And so that's going to be 298K. All right, so we end up with 298K, so that's going to be our T2. Our V2, our new volume, is at 400 mils. We put this in our calculator, and so when we do that, we're going to end up getting 186 Kelvin, or we're going to have to subtract 273, and we'll end up getting negative 87 degrees Celsius. All right, and so remember then, if you want to convert back between Celsius and Kelvin, you need to not add 273, you would need to therefore subtract 273. So delta C is equal to K minus 273. So if the problem asks for the temperature in Celsius, once you get this answer, which is in Kelvin, you need to remember to subtract 273 in order to get this in terms of Celsius. And so it's going to be negative 87 degrees Celsius was the original temperature. And so that is an example of a Charles law problem. All right, let us go ahead then and do an example of a Gay-Lussac problem. So it is very français, s'il vous plaît. All right. And so now we're going to look at how pressure and temperature are related based and holding the volume constant. And so for Gay-Lussac's law, it's going to be very similar to Charles' law, but instead of volume, we're going to be looking at pressure and temperature. So we're going to have P1 over T1 equals P2 over T2. And so this is representative of Gay-Lussac's law. Remember again, the temperature needs to be in terms of Kelvin. So remember, K is degree C plus 273, and that degree C is K minus 273. All right. And so let's take a look at a problem that involves Gay-Lussac's law. And so what we're going to be looking for is what is the new temperature of a gas at 100 kilopascals and 0 degrees C is reduced to 25 kPa. notice that we have a change in pressure, and so we need to then figure out what the new temperature is going to be. And so the temperature, as we can expect, is going to change as well. All right, so I'm going to go ahead, I'm going to solve for T2. So I'm going to go ahead and take P2 times T1 over P1, and that'll solve for T2. And so T2 is P2 times T1 over P1. And so again, I basically just rearranged this. I multiplied both sides by T1, and then I divided both sides by P2, and so then I was able to solve for T2. All right, and so let us go ahead and solve this problem. We're going to go ahead and set T2 is equal to our new pressure, which is 25 kPa. Our temperature, if you notice again, this is at 0 degrees C. We need to add 273, which makes this 273 K. So we'll put 273 K here. We're going to divide this by 100 kPa. And so notice that when we do this, the kPa's cancel out, so you're left with Kelvin, which hopefully should make sense. And so we end up getting 1092 Kelvin, or if we subtract 273 from that, we should end up with 819 degrees C. All right, and so remember, you first have to convert the temperature or temperatures to Kelvin. Once you go through the problem, then if it asks for it, then you can convert back to Celsius by subtracting 273 from the Kelvin reading. And so for this problem, we end up getting about 819 degrees C. And so that is an example of a Gay-Lussac problem. All right, what I like to do now, I want to go ahead and do a combined gas law problem. All right, and so a combined gas law fuses together Boyle's law, Charles's law, and Gay-Lussac's law. And so if we're going to go ahead and write that back up here. All right, so the combined gas law we have P1 times V1 over T1 equals P2 times V2 over T2. Notice again that the combined gas law looks at the pressure, the volume, and the temperature before and after for a particular gas. And so this again combines the three previous laws. All right, let's take a look at a problem. And so the problem that we have here, we're going to go ahead and just to make it easy on ourselves, I'm going to go ahead and I'll go and give you the actual units. And so what we have, we're looking for a new pressure. So what is the new pressure of a gas at 108 kilopascals in 500 milliliters at hold on just a second, at 283 K moved to let's do 750 mil and 294 K. All right, so the question here, what is the new pressure of a gas that was originally at 108 kilopascals in 500 milliliters at 283 K? It's moved then to 750 mils and 294 K. So I went ahead, I converted the temperatures to Kelvin just to save us a little bit of time. Notice that in order to solve a combined gas law problem, I would need to give you 5 out of the 6 variables, and then you'd have to solve for the 6th one. And so notice that in this problem, we're solving for P2. So I'm going to go ahead, I'm going to rearrange this. So I'm going to multiply both sides by T2 and divide both sides by P2 so that I can, or V2, so I can just solve for P2. So notice I'm multiplying both sides by T2 and dividing both sides by V2 to solve for P2. So P2 is going to be equal to P1 times V1 times T2 over V2 times T1. All right, and so again, I went ahead and recorded that as such. Now all I need to do is just plug in my numbers and then solve for the P2. So P2, our initial pressure is 108 kilopascals. Our initial volume is 500 mils. Our initial temperature was 283. The new temperature is 294 K. The second volume, the new volume, is 750 mil. And then the old temperature, the original temperature was 283 K. All right, and so again, I'm just plugging in what I'm told, and so I can put this in my calculator, and so the new pressure is going to be 74.8 kilopascals. And I also wanted to remind you that rounding errors will not count against you. So for example, if you rounded this up to 75 kPa, as long as you show your work and have the unit, I would still give you full credit. So again, we find out that the new pressure is 74.8 kilopascals. And so this is an example of a combined gas law. All right, let us now go ahead and do an example of a molar volume problem. All right. In order to do a molar volume problem, we have to know that the gas is at standard temperature and pressure. And so just to remind you, standard temperature and pressure, STP. So STP is at 0 degrees C and 1 atmosphere. All right, and so if you have a gas under standard temperature and pressure, we know that a mole of that gas will always take up 22.4 liters. So 1 mole will always equal 22.4 liters. And so it doesn't matter the type of gas, if it's nitrogen or carbon dioxide or oxygen gas, as long as it's under standard temperature and pressure, a mole of that particular gas will always take up 22.4 liters. And so let us go ahead and do an example of a molar volume problem. Right. So our molar volume problem is going to look for, calculate the volume of 0.54 mole propane at STP. All right. So we're told we need to calculate the volume of 0.54 mole propane under standard temperature and pressure. So we can use this relationship to help us out. And so we're going to use the conversion factor. And so notice that we're given moles, and so we're going to put the mole on the bottom so that the units cancel out. So we're going to go ahead and we'll do that. So we're going to go with 0.54 mole propane. And see, in this problem, we don't even care what the formula for propane is. And so if you're curious, it is in fact C3H8, but that will not factor into this problem because, again, we're only looking at it in terms of molar volume. All right, we're going to go ahead. We're going to put the 22.4 liters on the top so that the 1 mole of propane goes on the bottom. So 22.4 liters of propane and 1 mole propane. All right. Notice I set up this problem so that the moles would cancel out. And so all I need to do now is take 0.54 and multiply by 22.4. And so if I do that, I'm going to end up with 12.1 liter of propane. And so for this type of problem, again, remember that it has to be under standard temperature and pressure, which you can expect the problem on your test is going to be. Remember that a mole of any gas under standard temperature and pressure, STP, takes up 22.4 liters. We set up the problem. We put the mole on bottom so that it cancels out. 0.54 times 22.4 is 12.1 liters of propane. And so that's an example of a molar volume problem. All right, let us continue on then by looking at an ideal gas law problem. And so ideal gas relates a gas's pressure, volume, amount, and temperature using the very handy Pivnert equation. So Pivnert. All right. So Pivnert stands for P times V equals N times R times T. So P times V equals N times R times T. So remember, P is pressure, V is volume, N is moles, R is your gas constant, and T is temperature in Kelvin. Don't forget you have to always convert to Kelvin when you deal with temperature. So remember, for Charles's law, Gay-Lussac's law, and for the ideal gas law, remember to convert to Kelvin. All right, here's the setup for this problem. All right. How many moles of helium gas would be required to fill a 22-liter container at a temperature of 35 degrees Celsius and 3.1 atmospheres. All right, let me read you again the problem. So we're looking at an ideal gas. The question, how many moles of helium gas would be required to fill a 22-liter container at 35 degrees Celsius and 3.1 atmosphere? All right, couple things we need to do in order to solve this problem. The first thing we need to do is we have to always remember to convert to Kelvin. And so we have 35 degrees Celsius. We're going to take 35 degrees C plus 273. And so that is going to give us 308 Kelvin. So that's going to be our temperature. Also note, the gas constant R, remember, depends upon the pressure unit. And so notice that our pressure unit in this case is an atmosphere, and so our gas constant this time is going to be the 0.0821 liter atmospheres per mole K. Don't freak out. I will give you all three of those gas constants, and so you just have to pick which one to use for the particular situation. And so our R in this case is 0.0821 liter atmosphere per mole K. All right. So we have our temperature in Kelvin, we know which gas constant to use, and now we're ready to solve this problem. So notice that we're looking for the number of moles, and so remember, moles is represented by N. I can move the R and the T to the other side by dividing both sides by RT. N equals PV over RT. I then simply plug in what I know and then solve for the moles. So my pressure is 3.1 atmosphere. The volume is 22 liter. Our particular gas constant, because we're dealing with atmosphere, is going to be 0.0821 liter atmospheres per mole K. And then our temperature in Kelvin, we calculated to be 308 K. All right, and so if we plug that in our calculator, we will see that our answer is going to be roughly 2.7 moles for that gas. All right, so to recap, ideal gas law is Pivnert. PV equals nRT. I'm looking for moles, so I can rearrange my equation so it's N is equal to PV divided by RT. My temperature, I convert to Kelvin to get 308 K. I have to use the 0.0821 gas constant because it's the one that involves atmospheres. I plug in the numbers into this equation, and then I solve for the problem. And so that is an example of an ideal gas law problem. All right, one more problem, and then we'll be done with the review. So we are going to go ahead and do a problem that involves stoichiometry. So again, we're going to go through this and make sure that you guys understand it. All right. All right, we're going to go ahead and do a gas stoich problem. For this problem, and just like on the test, I will provide you guys with the balanced chemical equation. And so let me give you the equation. We have fluorine gas reacting with water vapor to form oxygen gas and hydrofluoric acid. And so if you wanted to check, you would see that the number of atoms on the reactant side equals the number of products on the atoms on the product side. So again, I would give you the balanced equation. All right, here's the question. If the reaction starts with 2 liters of F2, how many grams of O2 are produced at STP. All right, as soon as I say STP, what should hopefully pop into your head? You should think about molar volume. And again, a mole of any gas under STP is going to be 22.4 liters. And so we can use that to convert from volume to mole. So remember again, just like before, the first step in most stoichiometry problems is to look for the mole. And so we're going to go ahead and use that as our first step. We have 2 liters of F2. Because this is under standard temperature and pressure, we know that a mole of F2 is going to take up 22.4 liters. Units cancel out. We next need to go from moles of F2 to moles of O2, and again we need to use our balanced chemical equation. We use the coefficients out front to help us out with that. Notice that we have 2 moles of F2 and we have just 1 mole of O2. So we're going to put the 1 mole of O2 on the top, the 2 mole of F2 on the bottom. And so again, I was able to get this conversion factor using the balanced chemical equation, the 2 and the invisible 1 here for oxygen. So 1 mole of oxygen to 2 moles of F2. Then it's looking for grams of O2. And so to go from moles to mass, we need to know the molar mass of O2. Oxygen, approximately, according to the periodic table, is 16 grams per mole. O2, we need to double that. 16 times 2 is 32 grams per mole. We'll put the 32 grams of O2 on the top. The 1 mole O2 goes on the bottom. To solve this problem, we're going to take 2, divide by 22.4, divide by 2, and multiply by 32. When we do that, we should end up getting roughly 1.4 grams of O2. So notice that when we set up this problem, we see that it's at STP. That means that 1 mole takes up 22.4 liters. We use our balanced equation to get the mole ratio. And then once we have it in terms of moles of O2, we look at our periodic table to determine that there's 32 grams of O2 for every mole of O2. And so when we do the math, we end up getting 1.4 grams of O2. And so I hope that this was helpful, and I do want to wish you all good luck for the test tomorrow. Thank you.